All right, Chem 214 folks. I hope that you are doing well. This lecture is on spectrophotometers. Chapter 20 is where we are. It goes into a great deal more detail than I'm interested in. I'm going to give you the basic outline of a spectrophotometer and then a brief overview of what spectroscopy is. And then we'll move on to Chapter 21 in a different video. Okay, this one won't be too long. So we are interested in spectroscopy. Right? In spectroscopy, really what we're dealing with, this is chapter 20, by the way. In spectroscopy, what we're dealing with is interaction between light and matter. Okay. Now you have likely used a spectrophotometer. In organic, you use an IR to shine infrared wavelengths on your sample. Whatever that sample absorbs, you note as transmission dips, and then what it doesn't absorb, you note as transmission pass-through, that 100% transmission at the top of the graph. You may have used, or at least heard of, NMR, nuclear magnetic resonance spectroscopy. NMR spectroscopy is the same as an MRI that you may have had at the hospital. And it's radio waves interacting with the nuclei in a particular sample. By far the most common source, the most common method of spectroscopy that we see is in UV vis. And that is what we will spend most of our time talking about. We may talk a little bit about FTIR, we may talk a little bit about atomic absorption spectroscopy, but usually by far the most common is UV vis. Again, that's ultraviolet visible. This is by far the most common type of spectroscopy. And when we talk about UV vis, more often than not, what we're interested in is molecular information. Right? With NMR, we can get some information about the sort of the connectivity of molecules. With IR, we get some information about vibrations, if you remember that from organic. With molecular information from UV vis, mostly what we're getting is information about the electronic structure. Right? And the way those electrons are organized. One of the key points about UV vis spectroscopy, we will always see it as absorbance versus wavelength. And generally speaking, UV vis are pretty broad peaks, right? The normal range for UV vis is 400 to 700. It can be a little bit wider, really. I mean, if we're talking UV, maybe down as low as 200, 150 sometimes, depending. And up as high as 950, maybe. 950 switches to near IR rather than visible. And so, generally speaking, we stick to this 400 to 700. That's just the visible part of the spectrum. Sometimes we get down below 400 or above 700. But generally speaking, we have broad spectrum. What's happening inside a UV vis instrument is that we have some light source. That light source generates hopefully a very broad range of wavelengths. So this is our light source. We want a broad wavelength range. Because in an ideal world, we'll only have one light source for every instrument that gives us as broad a range as possible. For some UV-Vis instruments, that's true. For some, they do have multiple light sources. We talk more about that in 411. From there, that light gets focused down and sent through a monochromator. I'm just going to represent it as a big box for now. Monochromator, you can imagine, gives us a single wavelength. In reality, it's a very, very narrow band of wavelengths, but let's think about it as a single wavelength. And then we go through our sample. Right? This is a little cuvette with our sample. And then we have to have something to detect our the light that's given off. This is just a little eyeball from the side. Right? It's kind of a weird thing, but a lot of old textbooks do it. And I thought it was fun when I was a student, so that's what I do. Okay. So this is as basic as it gets. We have some light source. We select a single wavelength. Out of that wavelength goes to our sample, and then it hits a detector. What we want to know is how much of that light is absorbed and how much that light passes through. And so we have this, the intensity, naught, I naught, that's a little zero. Right? This is the intensity of the light with just the blank in there. UV-Vis is one of those experiments where we have to have a blank. We don't just measure against air because, of course, we don't want solvent. If the solvent absorbs anything, we want to know about that. If the cuvette that it's held in, the little sample container that it's held in, absorbs anything, we want to know about that. So we have to have some kind of blank with a UV-Vis experiment. And then we use normally just regular I for the intensity of light with the sample. Okay? And it's the ratio of these two that we're really interested in. Okay? Sometimes you'll see these as P naught and P for power versus intensity. Those are really interchangeable. Okay? Now, where do we go with this? Once we have those two intensities, what we do is we calculate the transmittance. And so the transmittance, just as it sounds, is the amount of light that goes through based on how much actually came in. And so the transmittance is I divided by I naught, right? Or P divided by P naught if you use power. Transmittance is often a T. And sometimes we write this as percent transmittance, and so we would multiply by 100. But for our cases, we want to keep it as T. Infrared uses percent transmittance when it makes a graph. However, most other types of spectroscopy use absorbance. Absorbance and transmittance obviously have to be related, and the method that folks have chosen to relate those two is logarithmically. And so if we take a look, absorbance, or big A, big A is equal to the negative log of T. And so we could rewrite that as the negative log of I over I naught. This value, of course, should be less than 1. And so giving the negative log here, we should get a positive value for absorbance. Because this is logarithmic, just real quick, if the transmittance is 10%, right, then A is equal to 1. If the transmittance is 1%, A is equal to 2, etc., etc. That's the logarithmic relationship. Generally speaking, when we look for good absorbance values. We want to keep it less than 2. Once we have less than 1% of the light passing through, there's more uncertainty there in terms of how much is really passing through. And so we try to keep our absorbances under 2, or at least under 3, even if we're using really high quality instrumentation. Okay? And so a problem would look something like this. A sample had a transmittance of 6.43%. What is the absorbance of the sample? Okay. Easy enough. The key thing here is to remember that when we have that equation, it's not A negative log percent T, it's A negative log T. And so the absorbance is equal to the negative log of 0.0643. And when we take the negative log of that, we get an absorbance of 1.192. Same logarithmic sig fig rules apply. We've got 1, 2, 3 sig figs. We just have 1, 2, 3 decimal places in the mantissa. Okay. That's it for the design and sort of the basic principles of spectroscopy. We'll come back later to think about Beer's law and some of the other aspects of using spectroscopy in later chapters. Okay. Hope you're doing well. Take care.